My talk today is on understanding the LNAPL distribution, mobility, recoverability in the subsurface, and the evolution of the state of the knowledge over the past 3 decades, and its impact on the legal requirement that we remove free product or LNAPL to the maximum extent practicable. Well, here's an overview of my talk. First, I will go over the theory of the distribution, saturation, all that of free product, basically light non-aqueous phase liquid, gasoline, diesel, all that in the subsurface. We're not talking about DNAPL like coal tar or chlorinated solvents. And then we'll walk you through what's mobility in the recoverability, what's their definition, how to determine them. And then I'll move on to review some of those historical regulations on the extent practicable. And based on that, we'll say our current understanding and some advancement we've made in the regulations in recent years and the strategies going forward. Here, I use this cartoon just to show you a general release case of the LNAPL. Typically from a USD tank or above, storage tank, whatever, when release occurs, it goes to eventually reach the water table. You have the main body, which is LNAPL free product here, and at the edge you have dissolved plumes, and above you may have a vapor plume. And there's a capillary fringe, and the thing is if we can detect any release right after it occurred, it'll be easy for us to remediate it. We probably just go there and dig the soil out. That's the best way. But unfortunately, most cases, when we found the oil in the groundwater, it was too late. It already got into this zone. So especially after the plume spread, it's getting tougher to deal with this problem. Now, let's look at some of the old theory of the distribution of oil in the formation, in the aquifer. It says if we gauge monitoring for the oil, let's say I assume this is 1 foot product in this oil in this well. The old theory tells you that your product is going to be in the soil column immediately surrounding this well at the same depth interval. Basically, it says there's no product above this air-oil interface in the soil, and there's no product below the oil-water interface here. So according to this theory, now I'll just play with some numbers here. Assume the thickness of this zone is 1 foot. And let's say its size is 10 square foot. It could be a diameter of 3-4 foot or something. And assuming the soil has a porosity of 0.3, and in this case, in this model, we used to think it's 100% saturation only in this zone. The volume, easy calculation, about 22 gallons. All right. Now, I'd like to walk you through a very basic equation for calculating the conductivity. This equation can be used not just for calculating oil conductivity. It's kind of a universal equation for calculating fluid conductivity in a porous medium. Gravitational constant, G, this one is the intrinsic permeability of the matrix. Has nothing to do with the product. It only has something to do with the process distribution and the soil material. This term is oil relative permeability, which is the relative permeability. This thing represents the fraction of the saturated LNAPL conductivity at a given saturation. All right. Relative permeability ranges from 0 to 1. When you have no fluid in the pore space, you get nothing, so that's 0. When you fill the pore space 100% with a fluid, the thing becomes 1. So it's sort of proportional, but the relationship is, most cases, not linear. It's curved. And the two other parameters here are the oil density. Oil density, water density, fluid density, depending on what you're going to use. And bottom is the viscosity. We use this screen sometimes because under standard conditions of water, the thing is 1 gram per cubic centimeter. The thing is 1 CP, so they cancel out. So, so that's why sometimes they call this thing. If you plug in oil water relative density and the relative oil viscosity into this equation, you get the oil conductivity. So you can easily use this equation to derive the oil conductivity relative to hydraulic water conductivity. So anyway, we know that higher saturation leads to higher relative permeability, and higher relative permeability will give you a larger LNAPL conductivity. Say, plug in this here, you get this. Now, based on that theory, we use the same example. We want to calculate the oil conductivity for this thing down here. Now, I do not want to plug in all the numbers to give you a real value. Let's just assume the LNAPL conductivity corresponding to 100% of the saturation is at its maximum. All right, and we'll talk about this a little bit later. Now, the actual situation, if you go out, take some soil samples, take to the lab, measure the saturation, what you're gonna say is something like this. It's hardly even close to the pancake type model. Well, sometimes, many times, you also get some measurement below the water table. What caused this thing? Smear zone, water table fluctuation, so that some of the products get trapped when the water table moves up and down. Now, I think I'd like to show you a couple of cartoons, which is pretty good to illustrate this saturation concept. All right. On the left, the pore space, more than 50%, majority filled with oil. And water, in this case, is a minority. This typically occurs when near the air oil water table, and typically when a large volume of oil release and rush to the water table, it pushes the water away out of the pore space to occupy that. Another case is on the right. This occurs, for example, when you flush the soil by pumping or whatever, you flush most of the product out of the pore space, but there's still something left in there. And those are at very low saturation. Now, a couple of physically, the real examples, which from the soil core. These are two wells from 7 feet to 8 feet below ground surface. On the left, under the UV light, you only see very sporadic lights, which are the fluorescences of the product. This means really low saturation. Right? On the right is another extreme. It's almost all saturated for the whole foot of sand with product. So that's just the real example. When you do this in the field, you get the core. You can do it. Either set up a black room, a dark room. You take a UV light. You do it on the field. You can do the log, or just freeze the core, whatever. You take it to the laboratory. Laboratory can do the picture. Do that over there. It's more professional if you do it in the laboratory. But anyway, now, after all these years of study, we come to the knowledge that the actual distribution or the saturation for the soil column that are in equilibrium with the product thickness in the monitoring well should look like this, which says your maximum saturation is around the air-oil interface. And there's something going up to the air. Basically, the saturation decrease gradually, capillary effects from that. And then it decreases gradually when it's approaching the oil-water interface. So comparing the old model and the current model, old model says for the whole 1 foot interval, you get 100% a big pancake layer saturated. Now you only have this curve. If you calculate the area under this curve, it's really small. Another important concept is the residual saturation. To put it in a simple way, which is if you try to remove the product from the formation, and you're not likely to get the saturation down below this line, which means there's a certain level of oil that's going to stay in the soil. You cannot get it out by conventional methods. All right, this is a very general situations for the relative permeability as a function of saturation. It has actually two curves, one for water, one for LNAPL. See, for the LNAPL, the saturation here on the x-axis ranges from 0 to 100%. You say that the relative permeability increase with the increase of LNAPL saturation. It goes up, it's now linear, some kind of a curved shape. And here, this part means you have irreducible water saturation. That water, it's really difficult to get water totally out of the pore space. So in that sense, you never get 100% product saturation in the soil, in the formation. And similarly, on the other hand, the water, there is something called, that we just introduced, the oil saturation. So the water will also not reach 100% in the pore space. What this means is if you have LNAPL and water both in the pore space, neither of them can reach 100% of their conductivity. All right, using current theory, we can make this calculation. Again, say all the others are same, thickness, size, porosity. The difference is saturation changes. It used to be 100%. Now if you do the calculation here, integration, calculate the area. Well, let's assume this is a triangle. So the area is about half of the pancake model. So we got saturation only 50%. You plug that in, you calculate the volume of the oil. You got only 11 gallons, which is roughly 50% of the pancake when you're using the pancake layer model to make the calculation. And another thing is the conductivity. We don't know exactly, because it's not strictly linear relationship. We don't know what the real value is. I just call it the conductivity is likely 50% of the case for the pancake layer model. You know, this means a lot. First, you think you go out there, you have 1 unit volume of product which you think can recover according to the old understanding. Now, you realized you have only half of that volume and is probably 2 times more difficult to recover. And that's a factor 4. So that changes our understanding of this thing very significantly. Well, these are the factors affecting the distribution saturation of product in the formation. Just quickly walk you through soil characteristics, process distribution, basically the capillary effects, pore entry head, all that information, and product properties such as density, viscosity of the product, of the LNAPL, and also the surface tension, interfacial tension. Another thing is LNAPL release history and migration conditions, which says the history of wetting and the drainage has an influence on the saturation and distribution of the oil in the subsurface. They have studied on this something called hysteresis, quite complicated. Also, changing hydrostatic conditions also play an important role in the saturation. When we do the theoretical model, we're assuming equilibrium conditions. Out in the field, when you build the oil from the well, the old balance will be broken, and now they are moving to a new balance, a new equilibrium condition. So that is dynamic process. So this thing is it changes. It changes all the time. Also, study indicate saturation is not something fixed for one type of soil or a set condition. It changes depending on the initial product thickness. There are many studies indicating if the initial product thickness or saturation in the soil, which is, I should say it the other way, the residual saturation in pore space is sort of proportional to the initial product thickness. The residual is proportional to the initial thickness. So it's not fixed like, say, 20% or 5%. It's actually, the actual condition is more complicated. But anyway, so these are just walkthrough of the major factors. Here we gave one example, which is a capillary effects. This type of plots usually called water retention curves. At the bottom, the x-axis, this is water contents, and y-axis is the section expressed in centimeter. Draw an analogy. You put a straw in a cup of Coke. You say that the Coke level is a little bit higher than the level in your cup. So that's a capillary effect. It sucks things up. And you can also think of this suction as some kind of a pressure head. Now, let's give an example here. This is a sand, and at this level, it's roughly equivalent to 5% water content in the pore space. And you have something like 100 centimeters, roughly 3 feet, which means if you can reduce if you have a box, a fish tank of sand, you make sure you do the calculation, you put in 5% of the water, 5% of the pore space water in that, you're likely to see moisture rise about 3 feet, something like that. So this thing has a lot to do with soil texture, basically the pore size distribution. The smaller the pore size, the difficult, smaller the pore size, the higher the suction. Basically, the molecules working on each other, the Whiting phase, whatever. So the physical, the attractions of between the molecules of the soil and the water is making this thing work. The smaller the pore size, the larger the suction. And in other words, the higher the pressure, the higher the negative pressure. So think if you go to the field, you try to dewater a sand column, let's say 20% water content, you want to dewater that, you at least need to overcome this much pressure in order to put something in it, either air or oil. So that gives rise to the concepts of air entry pressure, and water entry pressure, all that. Now, here's a relationship, which is the profile of gasoline for the same product thickness in a monitoring well. Now, at the bottom here is this oil saturation, 0 to 100%. Here is the elevation above the oil-water interface. It's basically 1 foot. In this case, we assume 1 foot thickness in a monitoring well. These are in a formation, the distribution of the saturation. For coarse sand, it can reach 90%. It's pretty much, it's a lot of volume there. For medium sand, 80%. Silty sand immediately drops to like 15%. Silt, even worse, like 5%, which is essentially, you have so small pore size, the pore throat, the size, the diameter, whatever, is so small. It's really difficult for the oil to overcome the pressure to get into the pores. Now, this is another relationship, which is a saturation profile for the same volume of gasoline, all right, for various types of soil. In this case, we put the same volume of product into the formation. Let's say we try it in different type of soils. And what you will say is for coarse sand, you're going to have only 1 foot, for example. We only have 1 foot thickness for coarse sand. You have really high saturation. For fine sand, you're likely to have 2 feet thickness in the well. So If you just go out there without looking at the soil, you think, okay, that well give me 2 feet product 60. This well give me only 1 foot. Well, that 2 feet must have more product. Yeah, not necessarily right. You have to look at the soil. So the clay suit, you might have 5 foot thickness in the well for the same volume of oil in a formation, right? Mobility. The mobility is kind of similar to conductivity. Sometimes people use them interchangeably. They're slightly different. Mobility is defined as a potential for LNAPL at a saturation that exceeds its residual saturation levels so that it can move and redistribute in a pore space, in a pore network. This is a pore scale concept because when we're talking about residual saturation, it's on a pore scale or at a single sample point. It's not for the whole plume. Whole plume, you rarely talk about the mobility because it's different. Mobility is different everywhere in the plume. You can talk about the average if you want to do that. That's fine. Another concept is inherent mobility, which is a ratio of the average LNAPL conductivity to the effective free product porosity. Well, let's draw an analogy here. Darcy's law for water migration, for water flow is like this. Darcy's law, we know the conductivity times gradient give us the Darcy velocity. If you divided that by the porosity of the soil, you will have a seepage velocity. So this thing here is quite similar. This is like water conductivity divided by water porosity. So it's just different in this case for oil. Anyway, so this it's a concept that a lot of people use in their calculation on the research. So a very important thing to remember is the LNAPL have a very high mobility doesn't mean it will move. It needs a gradient. Simply like it's just like water in aquifer. If you fill a bathtub with water, it's not going to move because it doesn't have the gradient. Well, it has a vertical gradient, but it's not going to move. It doesn't have side gradient, so it's not going to move out of the bathtub. However, if you drill a hole on the sidewall, you create a gradient, it starts to move. So this same concept applies here for oil. And for plume, on the plume scale, we talk about stability. We typically use the word stability to describe LNAPL plume. We call it either stable plume, unstable plume, migrating, shrinking, all that things. So it's a different word and sort of different meanings. Now here, just to show you the mobility as a function of apparent well thickness. One thing you can say from here is, regardless of the product type, the mobility increase with the increase in the well thickness. And but for a specific well product thickness, you see the difference in mobility for the different types of product. That's can be explained from the relative permeability and also the viscosity of each of these products. So, okay, just using this equation, assuming this KRO is not changed for this case, and the density is neglected, it's not much different. It's the viscosity. You see that there's several times, the diesel several times higher than gasoline. The fuel oil number 2 a couple times higher than diesel. And the fuel oil number 4 is really 23, which is like 23 times the water, several times higher than the fuel oil number 2. That's why you have the relationship like this. Now, this is to look at that sort of a relationship in a different way. It's a mobility of a gasoline for various types of soil. And again, when product thickness increase, the mobility increase, no matter what soil you're going to have. Again, there is a trend which for soil with a larger pore space, larger particle size, it's easy, oil is easy to flow in it, so you're going to have a larger mobility. And vice versa. for the soil, which is really tight, really small pore size, and oil is going to move only very slowly there. I like to use this in very classical scenario to describe the difference between LNAPL mobility and plume stability. Here, we have the blue lines represent the potentiometric heads. Okay, here we got a 4 feet drop. Here we have only 1 foot, 4 feet drop. So the gradient on the left, on the right case, is 4 times that of the case in the middle. And also, say we, Dispenser Island, we take a sample in the middle of the plume. We found the residual saturation is below, the saturation at this point is below the residual saturation. So that means the mobility at this point, basically it's not mobile. It's below the residual saturation. You cannot call it mobile, so it's not mobile. LNAPL is not mobile in this case. And here is way larger than the residual saturation, so LNAPL is potentially mobile here. Again, LNAPL is mobile at this point, but will this correspond exactly to the plume stability? You know, in this case, you could say, well, plume is not moving. And in this case, you say, okay, plume is moving because we have this. Plume is moving, not always like that. So these are the results. Even if you have a large gradient, your saturation is just too low. So you got conditions here, plume is stable. Here, plume is also stable, even though you have a mobile LNAPL. Here is unstable. It's going to move because you have both a large saturation in the soil. Also, you have the enough gradient to allow the product to move. Right? Now, what is LNAPL recoverability? We define it as the ability to extract LNAPL from soil matrix. We know that LNAPL below residual saturation is not recoverable. Conventionally, just flushing with water. If you hit it, you become vapor. It's a different story, right? Then LNAPL at low mobility saturations is really difficult to recover. And a lot of study indicating these two things combined together sometimes account for 50% of the oil. So 50% of the oil is either below residual saturation or at very low mobility, so that's really difficult to recover. So eventually, a lot of your oil will stay there for a long time. Recoverable LNAPL may be present in both stable and migrating plumes. Migrating plume is easy to understand. You have a large volume, you have a high gradient that's moving, so you know it's easy to recover them. But stable plume, it's a stable, how can you recover LNAPL? Stable, as long as it has high enough saturation, you can create the gradient so that it will move. Depress the water table, use vacuum enhanced recovery, all that things will allow you to recover, even for a stable plume. Now, how do we estimate? Calculate these things, all these parameters, saturation, mobility, oil conductivity, and recoverability? Well, laboratory measurements, you take the core sample that can tell you the saturation. And also give you some other parameters. You can run some capillary effects of the soil, process distribution, you can do that. And then you can, using the theoretical relationships, all the equations there, to give you estimate of mobility and so on. And in field, you can do it using Bayes-Down test, which will give you the oil transmissivity or conductivity on a field scale. Also, you can do a recoverability pilot test, just to try really hard, use a certain method to see how much you can get, how long this thing can recover, and if this thing is going to be sustainable or not. So you can do that. And another way is to do it in modeling, 2D, 3D, and either analytical or numerical models. You can do that. Now, here I'm going to review an old study many years ago conducted regarding the LNAPL recoverability. It was conducted by ESNT, Environmental Science Technology, very old firm now. I think it's part of GES, using a proprietary model called ARMOS, very powerful model. Problem is it doesn't since it doesn't have graphical interface, you have to do the pre-processing and post-processing there. Well, anyway, I happened to be in a company for a short time some years ago. I used that on a couple occasions. Well, it's no fun. It takes a long time to run because, you know, you have to use really small time step on all those, solve so many equations. So it takes a long time. You turn it on, you go back, and the next morning you come back, it's probably finished. Anyway, so this study was conducted to identify conditions in which LNAPL is or is not recoverable. You know, this thing, it's not black and white. So what is like, how much is much? How enough is enough? So you have to draw a line there to make a definition. So in that study, it says, okay, we'll define not likely to be recoverable as less than 10% volume of the initial volume. So if you try really hard, you can only get less than 10% of the initial volume recovered, then it is called not likely to be recoverable. Otherwise, it is recoverable, potentially recoverable. All right. The situation is here, use one extraction well in the center of a big plume, and we located the pump 3 feet below the initial air-oil interface. Initial condition is a flat water table and constant product thickness. Let's do this. Well, okay, so this is a model domain. It's quite large. Diameter is 540 foot. Basically, that you know, that's also define your radius influence. It won't be more than that because you can set boundary conditions. They put a wire in the middle, and in this modeling study, they evaluated sand, sandy loam, several different types of soil, different types of product, and for the four types of product thicknesses. So you time all this together, give you 100 simulations. All right, so this is a perimeter matrix. The bottom is hydraulic conductivity. Here you get 7 types, and dynamic viscosity basically corresponding to the various types of a product. All right, they run this model. They find, for example, under the case of apparent product thickness of 0.5 feet, they pump really hard. What they found, if you can recover more than 10%, you just use a diamond here. Otherwise, use cross. So you get this result for this case. And then you move on. You do another set simulations. 1 foot, and you got this thing, all right? And you do it on now for the 2.5 feet and 5 feet. So 5 feet, we use a different figure to illustrate this result. You know, this zone to the right is potentially recoverable. You can get more than 10%. Otherwise, you get less than 10% because your hydraulic conductivity of the soil is getting smaller. It's getting smaller. Also, dynamic viscosity is increasing. And after all these simulations, you can so basically generated this these plots to make it easy to understand. It has 3 factors on this figure. You have hydraulic conductivity on one axis. You have product thickness on the other axis, and then you have the different type of products. Basically says the area red of each curve are potentially recoverable conditions, and anything to the left, the area to the left of each curve indicating is not likely to be recoverable. So I'll give you an example. This 1 to -3 centimeter per second roughly corresponds to 2.8 feet per day. So that's like Sooty sand or sandy suit case. In that case, for gasoline, if you have like a 0.7 feet of product in a formation, you probably can recover more than 10%. This is a critical point. You know, you can do this for the other things. Anyway, this provides a quantitative evaluation of the recoverability. But you know, there are a lot of factors to play with. What if I define 5%, right? 5%, then it's going to be different. And also you change some other parameters, it's different. But it just gives you a sense of the thing. Now, recover LNAPL to the maximum extent practicable. We know this because the environmental law requires the circular, you know, the late 70s, early 80s, they dictate this. And those were up to the regulatory agencies like EPA and the state boards, whatever, to make the decision as to what constitute maximum extent practicable. Problem is there are few specifics on this rule. It didn't tell you what to do. You say, well, you need to try. It doesn't have very good information on that. As our knowledge evolved on the LNAPL distribution and saturation in the subsurface, the practice related to recover to the maximum extent practicable also evolves. Okay, right now we're moving on a direction towards a set specific cleanup goals rather than a statewide. It's the fixed goal. So that's where we're going. And I'll give you some examples. What are the extent practicable things they are? Five examples here. You can tell which one is better than the other. So I'm not going to say which is bad, which is good. So they're just some is better than the other. Selecting maximum allowable parent well thickness, remediate to residual NAPL saturation, recover until NAPL removal is not effective, demanding a series of remediate methods until all options have been exhausted, or recovering until NAPL plume expansion or migration has stopped. Well, 1 and 4 is probably not that good. The other 3 are a little better, but there are big room to, you can push as a consultant, and the regulatory can push it back. But relatively speaking, 2, 3, 5 is more reasonable than 1 and 4. Now, some old regulations, pretty much in the 90s when each of the state defines regulations, you do say Georgia 1/8 or 1/8 inch, and this you have to reach 0.1 gallon per month for 12 months, which means you work for a whole year, recover only 1.2 gallons. That's tough, right? And also, some of these are kind of reasonable, but most of these things are using a arbitrary maximum allowable product thickness. So based on our current understanding of the thing, it's not very good practice, not very good rule. So extent practicable. We now know that this thing is set specific. We need to identify remediate goals that is achievable based on set specific information. Okay, we need to have a good set conceptual model. Then we need to know the saturation, volume, mobility, recoverability, all that. Also, you need to consider the risk thing. Say the LNAPL is very well contained or treated. Well, what about the vapor and the dissolved phase? Would they be causing a problem? And exposure pathway, receptors, all that. So how to consider all this? Then based on the set information, we can then implement some appropriate management strategies that are going to be effective and efficient. And then we're going to reevaluate the site conditions change. It's a dynamic process. Sometimes it's an iterative process. It's just never stop. When things change, take a look at it. Maybe you have to adjust your model, your conceptual model, or even your strategies to remediate the thing. Set specific goals. We already have some progress in that. California, in my opinion, is quite stringent, but they do have this low-risk foreign water sites, UST, based on all the study that says petroleum hydrocarbon is going to be naturally attenuated. So if at some location you don't have receptor, you don't have exposure pathway, you can close it before the concentration reaching certain state limit or the drinking water level, whatever. So that's a good thing. And Texas, they have new gas means compared to the old 1890 guidance. It's good. And Wisconsin also similar risk-based decision guidelines also on each individual cases. Basically, the site owners negotiate with regulatory agencies. In all those cases, they also have the site-specific cleanup goals. Now, show you a case study relatively fast. We have a former truck maintenance facility here in California. Formation, fluid, volcanic fluid stuff. It's basically all the boulders, gravels within a clay matrix. There's water table near the bottom of this formation. And according to our hydraulic test, all that information, it doesn't behave like porous medium. It's pretty much a fractured system. All right. LNAPL is present in wells around and former abandoned mine shaft. But immediately outside of this zone of LNAPL wells and downgrading of that, we don't really observe dissolved concentration, no free product. Now here's a map. So this zone are the LNAPL extent. So the wells surrounding it really close, has not been showing either product or dissolved impacts. So, well, this is a look at it in the cross-section way. These wells are screened in a deeper aquifer. So basically, these wells are screened in our formation of concern. These blue tubes represent the historical range of the LNAPL. So it's as high as this, and this is likely a purge condition. It goes out. Instead, it goes to this direction, which is following the apparent hydraulic gradient. It can also go back. And then we come up with this model, as a conceptual model. I think it's a fracture system. Waste oil dumped in through here. It goes out, penetrate into the fractures and move down. Okay, and then I was trying to estimate how much volume is in the thing. I'll go find some literature, the fracture porosity from all literature, and then I get some values from this literature to help me calculate the volume of this thing. Consider several scenarios for the zone of influence. We give us volume of the soil of the rock. Then use the saturation. Consider different saturation values in the fractures. Also use consider a range of values for the fracture porosity. We calculate the wide range of numbers of the volume, but we do know we have recovered more than 1,500 gallons so far. So according to the calculation, there's more. There's more out there. Also, we plot these figures, found out that the recovery has not even close to reaching the asymptotic conditions. So if using the maximum extent practicable standard to judge, we have certainly not reaching that level. So obviously now we have got to work harder. So right now we're considering doing some further investigations and maybe some product recoverability test on that. So this is not to say we have solutions, basically to share the information that is quite difficult. We're not even 100% sure what to do. Just working on it. Well, this is a summary. The distribution and mobility of product in the subsurface depend on set-specific information: soil properties, product types, thickness, and hydrogeologic conditions. All right. Then the recoverability should be evaluated on a site-by-site basis. So according to that principle, the remove LNAPL to the maximum extent practicable also needs to move toward the set-specific goals corresponding to the current state of the knowledge. All right. Some progress has been made, which is a good thing, but remains a lot to be done. And that concludes my talk. Thank you. Any questions?
Are there any questions in the audience? Yes.
Meng, during your presentation yesterday, you showed a case where there was LNAPL below a confined layer.
Right.
And the LNAPL was below a confined layer, and when you put a well into that confined layer, you have a much greater apparent thickness in the well because it's under pressure.
Right.
How do you think that product got below the confining layer in the first place? I have always not been able to understand that, because I have seen it in the field too.
It's I can look at this from several ways. So the confining layer, let's say, it may not be spatially continuous. There could be holes, connections. So the oil, when it's releasing at a great height and gradient, it will penetrate through those more permeable zone into the confined layer. So basically, you have to find a way for the oil to get there. The water may not be under pressure all the time. See, historically, if you pump too hard or the water table fluctuation in history, the potential metric level could drop well below the base of the aquifer, right? In that case, the confined aquifer becomes an unconfined aquifer. So all you are free is they find a hole in that aquifer to flow on top of this water table. And then with time changes, when water level recovers, the whole thing becomes under pressure. Then that happens.
Any other questions before we move on?
Is there a way of relating product recovery with plume stability? I mean, can you infer by your product recovery that you don't have a stable plume?
So can you rephrase it? Because
I'm wondering if you can determine. Well, you can make a statement about plume stability based on your product recovery.
right.
If you continue to be able to remove product freely, can you make some assumptions about not having a stable plume?
Having stable plume. Okay, I think it's this. You look at the stability of the plume. Basically, you can do that by looking at the thickness in the wells over time, right? So that's one thing. And but if you can tell the plume is stable, it's not moving. But if you have significant product thickness in the middle of the plume, which typically means you can recover more. And
Yeah, I'm just familiar with situations where we don't have a very good well network, and our ability to put in more wells is somewhat, is limited, and so therefore we can't define the plume as best as we would like, and so then if we can continue to remove product, can we make some inference about the plume stability?
okay, so you cannot make any recovery you think is going to be stable, or you want to propose this is stable, this plume is not posing any problem?
Yeah.
Need to collect enough evidence. More wells demonstrate the thing in a statistical thing. They require quality monitoring for 3 years to give you 12 samples so that you have enough statistical power to tell a statistically significant difference. Same analogy here. You have to have enough data.
Yeah.
But in some case, we push. So depending on the regulatory, they say, okay, we think this is it. They may say, makes sense. You're there. Otherwise, they say, no, you can't do more. So it all depends.